Welcome back, everyone. I hope that you've had a happy holiday season, a great New Year's, and that you're eager and ready to learn because I know that I am. So, in comparison to how I covered Introduction to Electrodynamics, this setup is going to be slightly different as covered in a previous video. Um, but, it's still worth reiterating that this is going to be more lecture style. We're only going to do select topics that the authors have deemed um, where, every reader needs to know how to do, and maybe some additional supplemental material. The reason for that is because there's two main thoughts in how to teach quantum mechanics. One of them from the wave mechanics side of things, that's the Schrodinger differential equation approach. The other is from the matrix mechanics side of things, which Heisenberg made popular. And quite frankly, you're going to need to know both. There's a large group of people who dedicate proving the equivalence of these two outcomes. I'll gladly link some papers to that because it's fascinating to see. But one of the things that most authors do agree on is that you have to learn the tools of quantum mechanics by doing them, and then you can start to, once you have these tools under your belt, you can start to argue what interpretation is correct, or if there's some other interpretation that isn't even listed yet. There's a lot going on in quantum mechanics, and it's very difficult to teach just a pure conceptual argument style because there's so many ways to interpret. The main reason for that is due to the fact that there is a high necessity for statistical interpretation in quantum mechanics. Thus, probability plays a huge role in quantum mechanics, and that's, the start of all of this argument. And it's really cool to see the timeline of events, especially in the early 1900s, and reading through that. Um, Again, especially with the research that was done with regards to spectral lines and things of that nature with the atomic structures. So there's a lot going on. But because of the fact that there is statistics involved, we need to know what exactly are the statistical measures we use, and that's what this problem highlights pretty well. So without further ado, we'll jump right in. This is problem 1.1, and they're asking for the distribution of ages in example 1.13, compute the expectation of the event squared and find out what the expectation squared of the event is. For part B, we want to determine delta J for each J and use equation 1.11 to compute the standard deviation, and then use your results in A and B to check equation 1.12. Again, all of these come from Introduction to Quantum Mechanics, Griffith's third edition. I'll link it below, that way we can all stay on the same page. But let's dive into how to deal with these weird angle brackets. Alright, so for our solution, the angle brackets are really just asking what is the average or expectation value. If I have a data set, what am I expected to get out if chosen at random? Okay, so what that does is it takes into account the probability of the event happening with the event magnitude itself. In this case, it's what is the likelihood of getting somebody with an age listed in the set, so 14, 15, 16, 22, 24, 25, and how many times do they occur? So probability is what we first need to define, and that is what n of j over n is. That shows us the number of times a particular event happens over the total number of events. So we're going to just put this in one big fraction. So here we see that the number of times that somebody appeared to be 14 in this data set was one time. And you can see the color coordination keeping the things in order for us. And it shows that we have 5 people that were the age of 25. So we expect that with this distribution of numbers that we're going to lean towards the 20s versus the 14s. And sure enough, once we compute it through, our expectation of picking something at random is 21. We expect that if we pick someone at random in any population after this, that we get someone roughly the age of 21, which is weird because we don't even see 21 in this data set. So the expectation or the average can be something that's not even included in the data set. So that's one statistical marker. What we were asked for, however, was what is the expectation squared? So we have to square this result and we get 441 as our result for that one. Now, what happens if we want the event itself squared, or the functional expression value is the expectation of j squared, and so we just square every age, or the event. So 14 squared, 15 squared, and so on and so forth. You compute that through, and we get the expectation of j squared is equal to 459.571. Now, if you saw the little reel, we see that these two things appear to be random until we need to calculate another statistical measure known as the variance, and that's what we'll do next slide. So the variance in this case, which was equation 1.11, and therefore the standard deviation, is given by the variance, which is sigma squared, is defined as the expectation squared of delta j, which is equal to sigma delta j squared, probability, so on and so forth. So we can make a table and how to break this down. For the given event j, 14, 15, 16, 22, 24, 25, those are all the years that we have, years old, and the number of incidences, that was already summarized. What we need to do is, well, delta j is the difference between the event and its average. So for 14 minus the average of 21, we get a -7. Cool. The negative, however, doesn't make any conceptual sense here because there's no such thing as a negative year-old. So that's when we go into squaring it, and that's why we get the square here. So what we're trying to do is look at the, quote, spread of the information and the spread of the data, and that's what our variance is. So one more thing to do, just to match up this form in the summation, is take this delta j squared, multiply it by the number of occurrences, and then we get this column here. I use these tables a lot just because it keeps the operation simple, easy, and we have a discrete amount of data that keep it organized very well. All right, so lastly, we need to sum up that last column up and then divide by the total number of occurrences. And we see that we get 49, 36, the whole last column. And we see that our variance is 18.571. What this tells us is that the standard deviation is 4.309. And what is exactly the standard deviation? Well, that is telling us what is the spread from the average. So I could add 4.3 to the end to one side of the average. 21 plus 4 gives us 25. That gives us most of the distribution. I could also minus it, and I could get 21 minus 4.3, and that gives us, what, 17-ish, 16-ish? And that's towards the tail end of the distribution. So this tells us roughly how well the data is spread out. And what we can see now is that we can also find this not just from a table, but from using the expectation values, where sigma squared, the variance, was equal to the unit squared expectation minus the expectation squared, and you see that we get the bigger number minus the smaller number, which is very important. This order means a lot, and we'll see why in a couple questions. But this gives us 18.571. Sure enough, same thing that we get from our table and our statistical formulas. And then you take the square root of these things and you get 4.309. So both cases work out to be the exact same. The only thing to say here is to note is that we use these expectations pretty exclusively, so we're not going to see many of those tables in the rest of the book, although you could potentially make them if it helps you. But beware, statistics will be coming back in this textbook and in every other textbook. But for quantum mechanics, we need a good firm grasp on it. but also be aware this is the language and the kind of jargon and symbolism they use to work with. So let's get ready for a fun semester of quantum mechanics. See you on the next one.